Okay, hello everybody. I wanted to go and I wanted to give a lecture on derivations for various base excitations. I think I've mentioned a couple times that I disagree with the book giving you one example, which was this one. And there's a damper, so you can hear my dog groaning in the background because I woke him up. Where this is the example in the book that they give, and and then eventually what they find out is the ratio of the input excitation, which is y, its mass, its magnitude is, and the output excitation is essentially 1 plus 2 zeta r over 1 plus r, or 1 minus r squared plus 2 zeta r squared to the 1/2, and I can't remember if that is squared or not. Let me take a look at some other notes. Sorry about this. Where's the full solution? Yes, this is squared. Okay, there we go. So I jumped ahead a little bit in the notes that I had written out. And the problem with this, there's nothing wrong with the solution, but the problem is from kind of a knowledge standpoint, engineering standpoint, is that, okay, what if this isn't your exact solution, right? Like, what if this was your system? Oh, that's not a very good drawing. Where the damper was fixed. K, C, and X, M. What if that was your solution? Okay, is this equation still valid for that system, or what if you had something more complicated? Okay, so what we're gonna do is we're gonna derive we're gonna look at 4 different cases for the configuration. Okay, so we're gonna start with this one. This one's case 1. Then we're gonna look at case 2, where we switch the spring and the damper. Okay, there's our damper. That's our displacement y. So we'll look at this system. Then we're going to look at the system that's above. Oops, there's nothing fixed for this one. Mass, spring, damper. So this is the one. We'll also show you how the book gets its solution. Okay. And then what we're going to do is the last one we're going to look at is a very general system. Okay, so we're going to look at a system like this, where you have a spring and a damper, and then we'll call this a spring and a damper here, and then we have some sort of base excitation like that. So there's y. Okay, and then what we're going to do is we're going to call this the mass of the system. This is the spring constant system. This is the damping constants of the system. And then we'll call this KB for the spring for the input for the base, and CB for the base, okay? And what this system is supposed to represent is kind of a generic thing. Like KS, does this have to be a configuration? No. When you go and drive your equations of motion, this could be a KEQ, okay? So this could be very generalized, and that's not damper, that's supposed to be an S. Okay, for example, what if let's take something that might look more realistic. What if we had a spring and then a dashpot damper fixed, and that's K1. This is C1, and then right here we had a K2 and a C2 to fixed, and then we had some input to our system, well, that's y. Okay, and then this is theta, and then of course you have an L1, and then an L2 and an L3, whatever. We'd have this complicated system. So what you do is you take this part of the system, reduce it to something simple, or really just get the equations of motion, and it'll show you how using the equations of motion from this. Oh, that's not supposed to erase. The equations of motion of this and this have the same form, and you can go in and get your x over y ratios. Okay, so that's what we're going to do today. We're not going to do this version. I'm just going to do this generic case, because going from here to here, it's just generating the equations of motions, and everybody in this course has shown that they're really, really good at this. Okay, so let's start. I guess we've already started a little bit, but let's continue starting, I guess. And let's look at case 1. So once again, case 1 was we had a damper that was fixed, right? C, M, and then a spring. And that has a base excitation of y of t. This has a response x of t at our mass, okay? Now, I've shown you how to get the equations of motion for this in class, but the key thing to remember is the force of the spring is k of x minus y, or the energy in the spring is 1/2 k of x minus y squared. And if you went into the Lagrange from that, or that's not E, this is U, du dx, remember the Lagrange should be taken with respect to the degree of freedom. That would end up being 1/2 k of d of x minus y squared, dx minus y times dx minus y dx. Okay, so you end up with 1/2 k of 2 times x minus y times 1. Okay, so this ends up being k of x minus y. Okay, and we know what they are for the damper component and the mass component. So you'd end up with this mx double dot plus cx dot plus k times x minus y is equal to 0. Okay, and what we're going to do is we're going to gather the things that are x on the left side and put the things that are y on the other side. So it's mx double dot plus cx dot plus kx is equal to ky. Okay, so now here we have our equations of motion, which once we have that, a lot of there's actually a bunch of more work, but a lot of the hard work is done. Everything else is tedious. And remember, we are engineers, and we don't worry about tedium, okay? So we're going to assume our input is y equals cosine omega t. Now, it doesn't matter if it's cosine or sine. Everything works out pretty much the same. Or it all works out exactly the same, actually. Maybe the phase shift might be different. But everything works out. You can do the math on sine or cosine. It doesn't matter. And we are going to assume that our particular solution has the form of a magnitude x times cosine omega t minus phi. Okay? And there's always a phase shift. If c does not equal 0, you're always going to have the phase shift. The phase shift comes from the damping. Okay, and x dot p. So the velocity of a particular solution ends up being negative omega x sine of omega t minus phi, and then the acceleration of this particular solution is negative omega squared x cosine omega t minus phi. Okay? And now what we do is we take these values and all these values and we just plug them into the right spot of our system. So we end up with is m times negative omega squared x times cosine of omega t minus phi plus c times negative omega x times sine omega t minus phi plus k x cosine omega t minus phi, okay, is equal to k, and then this is double check, this is the time to make a mistake. That's a spring constant, so it should multiply by position. So ky cosine omega t, okay? Now I'm going to group this term and this term together, okay? And then what we're going to end up with is x times m omega, I'm going to rewrite this order, x times k minus m omega squared cosine omega t minus phi, plus, okay, I'm going to leave this as a plus right now, c times negative omega x sine omega t minus phi, okay, is equal to ky cosine omega t. Okay. Now, before we can continue, we need to be aware of or look up some important relationships, trigonometry relationships. Specifically, that cosine of omega t phi, and I'm going to put these in some different colors. I'm going to put the positive signs in green and the negative signs in red so that they are apparent, is equal to cosine omega t cosine phi, and then watch this as the sign changes like that, plus minus or plus sine omega t sine phi. What this means is, I gotta call equations of motion. These equations of motion led to, these kind of parameter system equations, which is kind of making a summary sheet. So these equations of motion resolve themselves to this, okay? And then setting x p, and we'll call this system 1 of t is equal to x1 cosine omega t minus phi 1, okay? Where the magnitude x1 is equal to y times 1 over 1 minus r squared plus 2 zeta r squared to the 1/2. And phi 1 was equal to tangent negative 1 of 2 zeta r over 1 minus r squared, okay? And for each of these systems, I'm going to make one of these summary pages. That way we can go and compare how the structure of our system impacts equations of motion, these intermediate equations, and the ultimate form of our position equation, okay? So let's take a look at system 2. Okay, so for system 2, we've switched the location of the spring, the mass is the same location, but the spring and the damper has switched locations. That's x, that's y, okay? So our equations of motions have changed slightly. So now it's mx double dot plus cx dot plus kx is equal to cy dot. And I'm going to leave it to you to go and do that derivation yourself. Okay, but this part's changed. If we do the same thing with xp of t is equal to x cosine omega t minus phi, and then y of t is equal to y cosine omega t, okay? And then y dot of t is equal to negative omega y cosine omega, not cosine, sine, rookie mistake, sine omega t, okay. Make sure it's recording audio. Yep, okay, good, before I get too far along. Right, and then our equations of motion end up being mx double dot plus cx dot plus kx is equal to negative c omega y sine omega t, okay? And now, of course, this has changed a little bit. Instead of being a function of cosine, it's been phase shifted to sine, okay? And I'm going to skip all the steps and go focus mainly on the simplification. So if we go to c minus a, where a, b, and c are what they were before, is cosine omega t cosine phi plus b cosine omega t sine phi. Okay, in the previous example, if you remember, that was equal to ky cosine omega t. Okay, but in this case, that doesn't exist. Okay, so it doesn't exist, that it actually equals 0. And then c minus a times sine omega t sine phi minus b sine omega t cosine phi is now equal to, before it was equal to 0 for the previous example, now it's equal to negative c omega y sine omega t. Let me move that over so I don't lose any letters. Equal to, there we go, sine omega t. Now there's probably a handful of you that are wondering, wait, we were here and now you did this, all this. How'd you get there? So just as a reminder, if we go back and you plugged in, we were, you have this equation, you do these derivatives, you substitute them in, okay? And then you group your cosines and your sines together. You do the substitution with cosine omega t minus phi. You put that in there, sine omega t minus phi, you put that in there. You end up with this log thing, okay? You simplify, or actually that's where we were. You end up with this log thing, okay? And then you group the cosine omega t's together and the sine omega t's together, okay? That's how we did it. You can go back and look at that part of the lecture again and do that again. But I recommend doing that step yourself, because if you don't do it a few times, you're not going to remember it. Okay? And then, so this is going to simplify. Again, so you end up with the cosine omega t, so c minus a cosine phi plus b sine phi is equal to 0, and then c minus a sine phi minus b cosine phi is equal to negative c omega y. Okay? So we'll go and we'll start with, let's pull these over to the next page. Copy. Paste. Okay. So let's go and start with this one right here and solve for get our phase angle. C minus a cosine phi equals negative b sine phi. Okay. And then take the cosine over, and then this b over. We're actually going to go into there. And you end up with tangent phi is equal to c minus a over negative b, and phi is equal to the inverse tangent of c minus a over negative b. Okay? And if you go and you do all the substitutions, you end up, remember, that ends up being equal to negative 1 minus r squared over 2 zeta r, okay? And that's been phase shifted, so phi is equal to, it's equal to tan negative 1, tan negative 1 of negative 1 times 1 minus r squared over, I'm just rewriting it, not doing anything. I'm doing a horrible job rewriting it. It looks really ugly. Here we go. Negative 1 minus r squared over 2 zeta r, okay? And if you look, now that's just a phase shift, right? So this is phi 2. If you looked at phi 1 from before, that was equal to tangent negative 1 of 2 zeta r 1 minus r squared, okay? So there's been a phase shift, right? This was for system 1, okay? There's just been a phase shift based upon the input, okay? Now let's go and go back to this equation. So let's label this equation 5 and simplify it. Okay, and we'll do that on the next page. We've got plenty of room, so let's pull that over. Copy. Paste, there we go. Okay. So now we'll do our substitution. So we have, well, actually we need both of those because we got to square them, of course. Rookie mistake. Let's get these both over here. Okay. So let's see, that's equation 5. Okay. So we'll call this equation 4, this equation 5. Copy, okay. And when we go and we're going to square 4 plus 5 squared. Okay, it's the same thing that we got before. I'm not going to work it out. You can look at the previous example, but you end up with this c minus a squared plus b squared is equal to c omega y squared. Okay. Then we do our put back c's, a's, and b's into what they were, and you get x squared times k minus m omega squared plus x squared times omega c squared is equal to c omega y squared. Okay. And you do the algebra again. We've seen this algebra before. I'm not going to do it. You end up with x is equal to y times c omega squared times k minus m omega squared plus c omega squared to the 1/2. And then, of course, we multiply everything by 1 over k squared, and this by 1 over k squared. Okay, and we've already seen this before. We know exactly what every little individual bit is going to do, and x is equal to y times 2 zeta r over 1 minus r squared plus 2 zeta r squared. Okay. So let's set up our summary slide again so we can look at everything. Okay. So, there's 2 m's in summary. Summary for 2, okay? All that we switched was, that's not a, yeah, that's the spring. That's the damper. Y, C, K, M. Our equations of motion changed slightly. Mx double dot plus Cx dot plus Kx is equal to Cy dot. Okay. Our intermediate equations just switched a little bit. Cosine phi plus b sine phi is equal to 0, and then c minus a sine phi minus b cosine phi is equal to negative c omega y. Okay. Then our particular solution for case 2 is equal to the magnitude x for this solution, cosine omega t minus phi 2, where x, let me write that a little bit neater, x2 is equal to y times 2 zeta r. Make that a little bit neater, bigger there. That'll make it help it. Zeta r times 1 minus r squared plus 2 zeta r squared to the 1/2. And then phi 2 is equal to tangent negative 1 of negative 1 minus r squared divided by 2 zeta. That's not a zeta. My zetas are getting worse. Zeta r. Okay? Okay, I'm going to take a break, get some water. Okay, so let's go and do system 3. Okay, and that was the system that the book did. Okay. Y, X, M. kc. Okay, so in this case, our equations of motion are just mx double dot plus cx dot plus kx. It's a little messy. Is equal to cy dot plus ky. Okay. Now we've already done the derivation on if we had ky over here and cy over here, so pretty much almost nothing changes except this side now becomes ky. Okay. Let's just make that a little bit neater. Okay. And we know what to do from here. We're going to square them. We're going to square each side, or square each equations. Equation 4, equation 5. We're going to have 4 squared plus 5 squared, okay? And when we do that, we know that these sines and cosines become squared and go away. These sine and cosines become squared and become 1 and go away. And then these and these cancel each other out. So we're going to end up with this c minus a squared plus b squared is now equal to ky squared plus c omega y squared. Okay. Actually, let me go back one quick step here. Okay, where this equation of motion becomes negative omega squared m x of cosine omega t minus v minus or plus negative omega cy, that's a negative, or x sine omega t minus v, and then plus kx cosine omega t minus v is now equal to negative omega yc sine omega t plus ky cosine omega t. Okay. Okay. Just so remember how to do that intermediate step, because that becomes important later on when we do a more complicated example. Okay. And now we can substitute in our c's, our a's, and our b's, and this becomes x squared times k minus m omega squared plus x squared times c omega squared is equal to k. Might as well gather these y's together. Y squared times k plus c omega squared, k squared. Make that a little neater. Okay, that's a squared. Now we can solve for x and take the square root. So x is equal to y times k squared plus c omega squared over k minus m omega squared plus c omega squared to the 1/2, okay? And then when we multiply everything, oh, here my pen's loose. That's why it's not writing. If we multiply all this by 1 over k squared plus c omega squared, and 1 over k squared times k minus m omega squared plus 1 over k squared times c omega squared to the 1/2. Okay, this becomes y times 1 plus, and remember, c omega over k squared, that just goes to 2 zeta r. Okay, squared. Okay, and then this becomes 1 minus r squared plus 2 zeta zeta r squared. Okay, so what do you notice about this, right? This was from the K, and this is from the C omega. Okay, so this was from the it's from K. This is from C omega, and they're just added together. Of course, I forgot to put them in the 1/2. So now we're starting to see a trend where if we looked at the summary sheet for this one, there's that. So I'm going to go back a few. Look at the summary sheet for this one. Those are our terms. Okay, so let's go make a summary sheet for 3. Okay, there's summary 2. Here's system 3. Okay. Summary for 3. Okay. And let's go. We can pull what we need. Well, I'll just rewrite it real quick. Right. This is wrong color. This is our system. Y, C, X. That's X, that's K. I wanted all this to be black. Come on. Color. Black. Okay. Our equations of motion is mx double dot plus cx dot plus kx is equal to negative omega c. Just leave it cy dot plus ky. Okay. Our simplified intermediate steps is that. Okay. Our x is this. Okay, and then I'm gonna skip the phase for this one. Okay. Here we go. Now let's look at system 4. So system 4 is supposed to be a more generic, even more generic system. Something closer to a real life system where you have inputs y, mass x, but also some parts of your system that aren't inputs. They just exist, and there might be constraints on your system. Okay, so we'll call this ks, cs, and this will be kb and cb. The s is for the system. We might as well call this ms for the mass of the system. Okay, let me pull up my notes, make sure I'm consistent with my notes. Okay. Okay, and then the equations of motion are now equal to MEQ x double dot plus CEQ x dot plus KEQ x is equal to CBY dot plus KBY, where MEQ in this case is just equal to M. CEQ is equal to CS minus CB, and then KEQ is equal to KS minus KB. Okay. Let me make sure that I have these signs correct. You know what? That looks a little. Should be. I feel like those should be pluses, but let's take a look. Let's make sure that these are correct. Okay. Okay. So let's go and do our Lagrange, right? Because whenever I take a shortcut and try to do stuff in my head, I can make a mistake. So what do we have? We have the kinetic energy due to mass of the system. We have potential energy due to Ks and Kb. We have dampening due to Cs and CB, okay? The kinetic energy of the mass is 1/2 msx dot squared. That's easy, okay? The potential energy of this ks spring is 1/2 ks squared. There's no dot there, just x squared. Okay, the kinetic energy of the spring at the base is 1/2 kb of x minus y squared. I'm pretty sure my notes have a mistake in them. There we go. Okay, and then the r of the system is 1/2 cs x dot squared, and the r in the base is 1/2 c base of x dot minus y dot squared. Okay, so let's take a look at, I'm going to pull these over. Well, I'll pull this over here, save myself some space. This over here, okay? Now we can do our Lagrange. So dt dx dot, that becomes msx dot, and the rest of these are zeros. d dt dt dx dot is msx double dot, the rest of those are zeros. And then dt dx, those are always zeros, or at least for the systems we're looking at. Okay, and then du dx. So let's do this first one, is pretty easy. It's just ksx. Okay. The second one looks a little more complicated. So dub dx is equal to 1/2 kb, that's just a constant, times dx of x minus y squared times dx dy, and dx dy dx. So this becomes 1/2 kb times 2 times x minus y times 1. So this becomes kb times x minus y. Okay, yep, I did have a sign the mistake there. Now let's do the rs1. So those are zeros, and dr dx dot. This just becomes csx dot. And then this last one, let's take a look. Oh, there's a typo right there. There we go. This has essentially the same form as this one. And if you do it, you're going to end up with cs or cb times x dot minus y dot. Okay. Now when we add all these together, we have msx double dot plus ksx plus kb of x minus y plus csx dot plus cb of x dot minus y dot, okay, is equal to 0. Okay, we're going to collect the x's on the left and the y's on the right. So we're collecting our system's response plus kbx plus, I'm gonna shift these around so it's in the right order. This is cs plus cb x dot plus ks plus kbx is now equal to cby dot plus ky. Okay. Okay, now here's your MEQ, here's your CEQ. MEQ, KEQ. So I did have a mistake. These are plus signs, okay? Okay. Now, for our system, we can let A equal to positive omega squared MEQX, B equal to positive omega CEQX, and C equal to KEQX. Okay, so this is what's really the reason I like showing this kind of generic system, right? Is you can see that our equations of motion are the same form. Our constants changed a little bit. Instead of just one value being on both sides, like it's not CB and CB, it's now a constant plus a CS plus CB, KS plus KB. Okay, so our constants on each side are slightly different. Okay, and that doesn't change too much how we go about solving the problem, but it'll change the form of the final solution, and it's going to make it a lot more generic so that we can use it for a lot more systems. Okay, so now we can immediately go to our simplified representation. Okay, that's pretty straightforward. We're going to end up with, and you can do this derivation yourself if you want, but you end up with C minus A of cosine omega t cosine phi. Actually, this is before the intermediate representation. Here we go, let's write it a little bit neater, times C cosine omega t sine phi is equal to KB y cosine omega t. And I'm going to make this green so it sits out, shows up a little better, okay? And then this becomes C minus A sine omega t sine phi minus B sine omega t cosine phi. Wait. I've got a typo here. Do I? This should be cos. I think this one's supposed to be cosine. Nope. It's correct. Sorry. I had it correct. Just checking my notes to make sure I'm not leading you horribly astray. Equals negative CB omega y sine omega t. Okay. So just to make sure to get that, and all we did was we applied these derivatives, okay, and then we expanded the cosine omega t minus ph's and the sine omega t minus ph's and collected the sine terms and the cosine terms together, okay. And the reason I wanted to show this is because on the next example we're going to go really, really generic. We're going to show how this generic example can be derived from what looks like a complicated system, and that really you're collecting the cosine terms, the cosine omega t terms, and then the sine omega t terms, and whatever these constants are, C minus A, B's, and C's, it doesn't really matter in terms of what the form of our solution looks like, okay? Okay, and that simplifies down to wrong color. C minus A times cosine phi plus B sine phi is equal to KB y, and then C minus A sine phi minus B cosine phi is equal to negative CB omega y, okay? And we're going to square these together, square and add them together, and it's just like before. We end up with C minus A squared plus B squared is equal to KBY squared plus CB omega y squared, okay? Okay, and we can go in and pull out our x's and substitute in our a's and b's and c's, and we end up with x squared times KEQ minus MEQ omega squared plus x squared times, and then b was CEQ omega squared. Let's see, omega CEQ squared is equal to KB, KBY squared plus CB omega y squared. Okay, So notice that this form this form on this side is all the same. Okay, whether we call it a K or a KEQ or whatever this value is, it doesn't matter to the form. And something that's changed is, okay, here we have KEQ and here we have KB. And what that means is certain things aren't going to fully simplify. Hi, Elise. Do you want to learn some vibrations in algebra? Yeah? No? Okay. Can you open that box for me? Sorry, my daughter came in. Okay, so let's go and finish solving this, and we're going to end up with x is equal to y times kb squared plus cb omega squared over KEQ minus MEQ omega squared plus CEQ omega squared to the 1/2. Okay? And I'm going to write this a little neater. EQ omega squared. Okay. So let's talk about the differences. Okay? In the previous examples, this K was the same as KEQ. They were both the same values. This time, KB and KEQ could be different values. The same thing here. This is CB, where down here this was C, and they were both the same value. This is the damping of the base, and this is the equivalent of the system, and they're different values. Okay. So what's going to happen is if we were to go through and multiply by the same thing we always do, which is multiplying by 1 over KEQ, 1 over KEQ on both sides. I'm not going to write that out. And we multiply that through. What we end up with is KB over KEQ squared plus CB omega over KEQ squared, okay, divided by 1 minus r squared plus 2 zeta r squared. Okay. Okay. And what we've got now is this is no longer equal to 1 because these could be different values, and this is no longer equal to 2 zeta r, which is kind of okay, but it'd be nice if this was also had an r instead of omega, so you can see how it changes as a function of where you are, where you're driving relative to your natural frequency. Okay, so what we're gonna do is we are going to take our system, and we are going to multiply it by CEQ over CEQ. Okay? Okay, and then we're going to take this CEQ, and we're going to put it inside up here. Okay, so to save myself some writing, let's put that CEQ in here. Okay, and we end up with CEQ squared times K, oh, I might as well just put it all together. CEQ times KB over KEQ It's still not writing very neatly. Let's just write it bigger, okay? There. CEQ times KB over KEQ squared plus CB times CEQ omega over KEQ squared, and then the bottom start remains the same. 2 zeta r squared. Okay, and then this right here, this is just equal to 2 zeta r. Remember, zeta is equal to CEQ over 2 KEQ MEQ squared, to the square root of that, okay? Okay. So now we have x is equal to y over CEQ times CEQ KB over KEQ squared plus 2 zeta CBR, so that's a new term that didn't exist before, okay, squared divided by 1 minus r squared plus 2 zeta r squared, okay? Okay, what you can see is if K and KEQ were the same, these would just go to 1, and if CB and CEQ are the same, that goes away, and those just go to 1, and let's don't forget our 1/2, okay? So now what we have is a really generic form of our system, okay? So let's take a look at that. Let's put the summary for system 4, okay? And there's our spring, there's our damper, there's our mass of the system, damping of the system, KS, that's the base, that's the damping of the base, this is the base itself, moving of y of t is equal to y cosine omega t. Here's x of t, which is equal to x times cosine omega t minus v. Okay, and I'm not going to solve for the phase shift because that's actually a whole lot of algebra that I couldn't figure out correctly. Sorry, but I'm really kind of more interested in this response anyway. Okay, our intermediate form was this. Okay, and then our final system was this, okay? So now we have these summaries for each individual system, okay? And don't forget our equations of motion, mx, okay? Equation of motion was MEQ x double dot plus CEQ x dot plus KEQ x is equal to CBY dot plus KBY, where in this particular case MEQ is equal to M, CEQ was equal to CS plus CB, and KEQ was equal to KS plus KB, okay? Okay, so now we have these really nice generics. Let's go and compare. I'll make one more summary slide summarizing all 4 of them, okay? So summary of 1 through 3, okay? Okay, and then so system 1 was this one, damper on top. YKXM. Okay, and for these summary slides, what we're going to do is we're going to define HI omega is equal to 1 over 1 minus r squared plus 2 zeta r. Let's make that a little neater. Okay, let's write that neater. Is equal to 1 minus r squared plus 2 zeta r squared to the 1/2. So we're just going to define this equation as HI omega, just to be consistent with the book. And there's other portions where that becomes more important, like when we have different types of excitations. Okay, in this case, X for system 1, we'll call this system 1, is directly equal to Y times the magnitude HI omega, like that, okay? Now let's take a look at system 2. Where we switch the damper y, c, k, x. Okay, here's system 2. In this case, x2 is equal to y times 2 zeta r to the 1/2 times hi omega, that magnitude. Okay? Okay, now we're going to look at system 3, which is just pure base excitation. C, K, M, Y, X, that's Y. That's system 3. X3 is now equal to Y times 1 plus 2 zeta R. I feel like, did I make a typo? Let me take a look and make sure I didn't make a typo somewhere. Yeah, I think this might have a typo in it. Let me take a look to system 2. Okay. Yep, I have a typo. Okay, system 2. System 1. System 2. Squared. Okay. Double check that. Look at the book. Yep, that's squared. And that should have a 1/2. Okay, summary 2 squared. Whew. Sorry about that typo there. Okay. That means, there we go. Okay. This becomes 2 zeta r directly times hi omega. Okay. And this becomes squared, okay, times to the 1/2 times hi omega, okay. And then let's look at system 4. Okay. Here's our base. That's going up x, m, ks, cs, kb, cb, and this was 3. So in this case, x4 was equal to y over ceq times, okay, times, let's take a look at my notes, make sure I don't make a typo here. Where's that? Okay. Times ceq kb over keq squared plus 2 zeta cb r squared to the 1/2, and then I need a little more room, times the magnitude of hi omega, like that, okay? So now we have this generic form, okay? And that's going to be really useful. So let's go and create a more complicated system so we can see what that looks like, okay?